acceleration of this point is P, acceleration of P with respect to center is alpha. So APC plus AC, if it is 0, then I get AC minus alpha is equal to 0, or AC is equal to alpha, if I define in this way. And also omega is also not there. Omega is also not there. If omega is there, then again I may have to take this pseudo torque. But when when the centripetal acceleration, when it passes to the center of mass, then the pseudo torque automatically becomes 0. For example, here the pseudo torque due to first is becoming 0 because that pseudo torque, the centripetal acceleration, this acceleration of P point was passing through the C point. Therefore, that will give us pseudo torque 0. But the one which is not passing through it, this acceleration was in this direction, but this point does not, this mass does not lie in that. That will be giving us pseudo torque, which will be not cancelled, which will still remain. Pseudo torque will not be 0 for that part. So in such cases, when A is already 0, then we can safely apply tau P is equal to IP alpha, because it is just inertial frame only, we can say, right? In those cases, we don't even have to worry. So we have to be careful that in those cases where the instantaneous center of rotation has some centripetal acceleration, then the pseudo torque due to that we should definitely take. Is it okay?
Yes, sir.
Right. Next question we can take. That is of, I think I should start somewhat for this week now. In this week we have, before going to this week, one question I can take before going to this week's syllabus. Again, one more question I will take. That is based on this is a vertical rod. Vertical rod suspended under a block, and there's a pin joint here, so it is free to rotate about the block, and the block is lying on a frictionless surface. There is no friction anywhere. This rod is of mass m, length L, this is capital M, and we provided it some impulse. What impulse we should provide so that it makes the complete circle around m mass? Can you do this so that it makes a complete circle around m mass? How to do this one?
Is fixed, no, sir?
That means we have to.
No, not fixed. It is fixed in the same case as before. These two are attached to each other, but this is frictionless surface. It is free to move. It can move. It can acquire horizontal velocity.
Okay, sir.
So to do this,
We can assume velocity v, sir. Initial velocity of
yes. We can assume initial angular velocity.
Change in momentum equal to impulse, sir.
If initial angular velocity is, this will be slightly more complicated if I ask in terms of impulse. That impulse given is, then it will be slightly more complicated. Impulse case I will take. And that initial angular velocity was given as omega naught. And this upper mass was given to be at rest. It was at rest initially. Then what will be the situation after long time? I mean, not long time, after when it goes to the highest point at that time. At that time, first of all, mass will be shifted slightly. It will not remain in the same location. It will be shifted. Will it be? Or will it remain there only?
Sir, he was going to apply conservation of momentum, sir.
Conservation of momentum we can apply or not, you tell me. What is the rule to apply conservation of momentum? Why are you asking me? You know the rules. What is the rule to apply conservation? Yes, is it 0 in horizontal direction or not? So in horizontal direction we can apply,
yes,
but
sir.
not in any other direction. Only in which direction we can apply? Only in horizontal direction.
Okay.
So I should think like this now, that it should be able to reach up to the highest point. But when it reaches up to the highest point, at that time kinetic energy not 0. No, don't say kinetic energy 0. At that time, this with respect to capital M, its velocity will be 0 with respect to capital M. But they both will be having some velocity because of conservation of momentum. Let us say its velocity is v and its velocity is v. And initially its velocity was v naught. V naught we can find by L by 2 into omega naught. Then I can write conservation of linear momentum along horizontal, because along horizontal there is no external force. So only along horizontal we can apply. As it's a frictionless surface, Other forces are internal, hinge reaction, etc. Those are internal. Only force connect from here, from the ground, and that will be normal upwards, and friction can be there, but it is not there because it is given frictionless. So there is no horizontal external force. So then this is small m and this is capital M. Then what do we get finally? M into V plus small m into V is equal to m into V naught, which is equal to m into L by 2 into omega naught. So we are getting V from here easily, equal to m by capital M plus small m into L by 2 into omega naught. Once we know this final velocity, next is conservation of mechanical energy. Can we apply COME? By conservation of mechanical energy, we can write, let me write here only. You write by that time I am arranging this, you please do it, finish it. By conservation of mechanical energy, we get another equation, and that will be, can you write, initial mechanical energy, initially
half IP omega square.
half of IP into omega naught square, that is initial. Finally, it raises height, potential energy increase MGL, and kinetic energy will be, now it will be just coming at rest with respect to the lower one. This rod is coming at rest with respect to this. Then it cannot have any angular velocity. It is just coming to rest because we are only just able to reach there. If it still has angular velocity, means we have given extra than required. So it should be just able to reach there. Then MGL plus half of M plus M into V square. That it will be. Why ending MGL? Because L by 2 below, and finally L by 2 above. Understood or not?
Yes, sir.
All right. Very good. Then next, I can ask another velocity here. What velocity we should give to it so that this capital M does not fly off the surface? When it will have tendency to fly off? If it goes to the highest point, let us say, or somewhere else also it will fly off. Then set pseudo force m omega square L, that may be equal to, that pseudo force may be equal to the weight of these two. Then the normal will become 0 and it may just tend to fly off. That may happen. So for that, I should give velocity more than required to just go at the highest point, or just to make the vertical circle possible. Okay. So if I give velocity more than the required for the vertical circle, then the normal may become 0. Right or not? Okay. Right. Next we have this week's syllabus now mainly, and in that we have conservation of, let me write the topics first. Conservation of angular. Yes, that is there, but what is not done till now? That is what I'm writing down. I know this is unit test. Conservation of angular momentum and
collisions also, sir.
Angular impulse and collisions. So don't think these are 3 different topics. I treat these all as single only. For me, these are not different. So yes, sometimes I can take definitely angular impulse cases in such a way so that angular momentum will not be conserved. But in many cases, there are both cases in the same only, means conservation of angular momentum is also applicable and angular impulse is also there and collisions are also there. So all also will be there in one place only. And I will be taking those examples first. So conservation of angular momentum first. Let us focus on first one, conservation of angular momentum. I will write conservation of angular momentum, COL, L for angular momentum. So to apply COL,
External torque must be 0.
torque, yes, very nice, very nice. External torque must be equal to 0. Exactly right. Then it will be applicable. So just keep this idea in mind. When external torque is 0, then COL is applicable. Now, you know, this very nice and interesting thing that I'm not saying that external force is 0. External force may or may not be 0. It may be 0 sometimes, or at other times it may not be 0. May or may not be 0.
Because due to that force, torque may or may not be 0.
Yes, because due to external force, torque may or may not be 0. Sometimes external force will be there. If external force is not there, if there is no external force at all, then we don't even have to think. When there is no force, obviously no torque.
Yes, sir.
Then automatically angular momentum will be conserved. But even when external force is there, then we have to be careful that external force may be there, but external torque may be 0. One more thing. If external force is there, sometimes it may happen that torque may be 0, but not about all the possible points. It may be 0 about some points, and it may not be 0 about other points. It may be 0 about some points, but it may not be 0 about other points.
Examples.
Example, yes, examples, numerous examples, you know. See, how many examples? You know already that force has this torque has this property that when the force passes through the, let us say this is the point, and about this point the force passes, and there may be some body here, and about this point it is passing. So about this point the torque is, angular momentum will be conserved. But what about point A? What about point B? You understand
Yes,
now?
sir.
Yes,
About
sir.
A and B, it will not be conserved. So it depends, because torque may be 0 even when the external force is acting. About some points torque will be 0 due to that external force, and about those points
So
definitely angular momentum will be conserved.
So we have to consider that point, sir.
So yes, we have to find, in fact, we have to find out that point. We have to look for that point always. The quickly you are able to find out that point or those points, it will not be single point. It will be a single line. And the moment you are able to find that line on which about some points, the angular momentum will be conserved. Sometimes it may be line, sometimes it may be a point also. When it will be just a point. When there are
Yes,
multiple forces acting, F1 acting and F2 acting, then where the two lines of forces are meeting here, then about P point the torque will be 0. So that will be just a single point only. Sometimes it is a single point. Sometimes it is not a single point. Sometimes it is a large number of points. So whatever it is, but we should look for that point, and then we can apply the conservation of angular momentum. And the way we say that linear momentum sometimes is not conserved, but Px may be conserved, Px may be constant if Fx is 0. Same way here also something like that we can do, that sometimes angular momentum may be conserved only in one particular direction only. In that direction, the torque will be 0. So if torque is 0 about an axis, net torque may not be 0. For example, this is a point here, and this is the axis, and torque is perpendicular to this axis. So torque is acting to this axis, and what is the component of the torque about the axis? 0 or not?
Yes, sir. 0, sir.
Then component of torque about axis will be 0. And if component of torque about axis, here component, this is axis here, unit vector along the axis. So, and this is a point about which the torque is T. So component of torque about axis, if it is 0, then angular momentum is constant about
That axis.
So total is not constant, but about that axis it is constant. This also may happen. There are some examples where so means that I told you, one idea I shared with you, that first of all, if external force is not 0, don't worry. Then also we can find out that some points will be there about which the angular momentum will be constant, because there will be some points about which the torque will be 0. So that is first thing that we should remember. Even when external force is 0, so try looking for, what is the key idea? Try looking for points about which torque external is 0. And once we are able to find those points, then we can apply, after finding that point, we can apply the conservation of angular momentum. So this a skill you have to develop. You should be able to find it out quickly. Second thing, that even when torque external is not zero about any point also, but it may still be zero about some axis, because when net torque is acting in this direction, then about some axis it will be still zero. This is example. This example we can take. I think I will not write it down. And another example I'm just giving it here. That, and this you can remember, that angular momentum will still be conserved about some axis. It may not be conserved, but its component may be conserved. So if total angular momentum has three components, Lx, Ly, and Lz, and if torque about x-axis is zero, then angular momentum about x-axis will be constant, right or not? Okay.
Sir.
Right. There are some other things which we can keep in mind, and we are borrowing those things also from our knowledge of circular motion and the forces and the momentum. When the force is acting perpendicular to the direction of velocity, then it is not able to change the magnitude, but it changes only direction. Same way, exactly same way we can do for. So it is like, and torque is acting. I am not saying torque will be acting in this way towards the center. We can have some situations where torque may be perpendicular to angular momentum. When torque is perpendicular to angular momentum throughout, then what that torque can do only, that can only change the direction of angular momentum, but it can never change the magnitude. This torque, which remains perpendicular to angular momentum at all instants of time. It is not like for one instant you see and then start making confusion. That will be mistake. At all instants you should see that is it same thing or not. At all instants of time, will cause only change in direction, of angular momentum, but will never change its magnitude. Is it okay? And this is just analogy. Analogy means similarity between our force versus velocity case, and I think I should write force versus momentum case, or if I'm writing velocity, then here something else I have to write, but there is nothing equivalent to velocity here. Even angular velocity is also not equivalent to velocity. Why? Because here we write just mass into velocity and we get quickly momentum, but here L has many terms. What are the terms for L? R cross m into VCM plus ICM into omega. But yes, if it is something like IP into omega, then we have analogy. Then omega will act like V and m will act like P in the IP. Okay, but wherever we can apply IP into omega, can we apply IP into omega always? No, we can apply IP into omega only for which cases? Where P is the fixed axis of rotation. So if it is about some fixed axis the body is rotating, then we can apply that. Now you may say, sir, you told that we can apply about instantaneous also. Yes, we can apply about instantaneous axis of rotation. But in that case, first of all, we have to be careful that here I said that this should happen at all instants of time. So means that point should be at all instants of time, it should be fixed axis of rotation. And if it is at all instants of time axis of rotation, then that is becoming now fixed axis of rotation only, right or not? I lost you. Hello.
Yes.
Oh, okay, right, fine. So did you get it? Hello.
Somewhat little bit confused.
So we are just building up ideas. Don't worry. I will come to examples. You will understand everything clearly. In fact, what is confusion? Tell me. What is the confusion? Tell.
Here, the direction
What is the confusion?
Sir,
Ask it.
so that means only we here we can conserve.
Yes.
That is the whole point you're saying about all this.
Say.
Clarify.
Yes, I am discussing mainly that we can conserve the angular momentum. But in this last case, I'm saying we cannot conserve, obviously. How can we conserve in last case? This is different. Before this, it was conservation, but it is saying, I'm saying here, we can have some, I want to give you a better idea of angular momentum. I'm saying that the way we have this momentum, and this momentum, if I apply force perpendicular to that momentum, then that is not conservation of angular momentum. That is conservation of magnitude of angular momentum only, I can say. It is like conservation of magnitude of angular momentum, but it is not conservation of angular momentum. Okay. Last is not example of conservation of angular momentum.
Understood.
Right. It is just conservation of its magnitude. Okay. Now, quickly, I will give you several examples, and that will make 100% clarity. It will make, and you will be understanding the things properly. So, what are the situations we will be facing while we are applying the conservation of angular momentum? I'm discussing all those situations quickly. Very quickly, I will be explaining all those. First of all, I will be making few diagrams, and which I will not be able to make very nicely, but I will try. Good enough. Don't worry, just you can keep on drawing the diagrams if you want, and I will explain all of this quickly. But let me make some diagrams, and I think you are understanding also somewhat. First case is a man is holding dumbbells, and the platform is rotating with angular velocity omega. This platform is free to rotate.
Yes, sir, it is audible. Yes,
Ah,
sir,
right.
yes, sir.
And the second case is where one disk and the other two disks are there. One disk is, these are also free to rotate about the vertical axis. This pole, this is like a pole about which these are free to rotate. But this pole is fixed to the ground, and ground is also frictionless. So there is no possibility of any torque. The torque cannot be exerted from the pole because it is free to rotate about the pole, and torque cannot be exerted from the ground as the ground is frictionless. But in between these two disks, this upper disk and the lower disk, there is a friction. So as I slowly lower down the upper disk on the lower disk, their angular velocities were different. One has omega 1, other has omega 2. But after some time, they will one will accelerate, other will retard, and they will acquire same angular velocity, same omega. So I can say overall net external torque is 0 here also. In this also, net external torque acting from the ground or from any other place will be 0 on these two together. Similarly, on this, when the man is holding dumbbells and when man will be pulling his hands out, pulling his hands in, when man will be pulling his hands in, then what will happen now? Moment of inertia will decrease. If moment of inertia decreases, what happens to omega? Omega will increase because I into omega will be constant, as this is also free to rotate. This platform was conservation of angular momentum. Shrinking Earth. Now Earth is free to rotate about its own axis, and there is no torque acting on the Earth. Otherwise, the angular velocity of Earth will keep on changing. We know angular velocity of Earth is always same. The duration of Earth about its axis is constant. But suddenly Earth shrinks, let us say, somehow, because of maybe there was some vacant space inside, imaginary situation, hypothetical situation we are assuming, and Earth shrinks, and radius of Earth suddenly becomes from R to R by 2. When that happens, then what happens? Moment of inertia will become less. And if moment of inertia becomes less,
Omega
omega
becomes
will
more.
become more. Then time period will become less. Duration of day will become less. So days will be of less duration. Now you may think that this is completely hypothetical example, and we never have such practical situation. Why are we dealing with such examples? First of all, one reason, we want to understand the conservation of angular momentum properly. Second thing, for Earth it may not be true, but it is definitely true for several other objects. There is something called as supernova explosion. You may not have heard of it, or some of you may have heard of it. Supernova explosion, what happens? In that case, the star, without supernova explosion also, sometimes what happens, when the star will reach its different phases of life, there are some phases in which star will expand, and there are other phases in which star will collapse. As the star collapses to a smaller radius, then moment of inertia becomes very, very small, and omega becomes very, very high, and there is something which then those stars do. Those stars will be rotating with such a high omega, and they have some magnetic field also. For example,
Like black hole, it will
also
become.
magnetic field, and those stars are also having magnetic field, and their radius becomes very less. Neutron star is something. Neutron star. What they do? They will be rotating in such with very high angular, with very, very high speeds. Their time period will be sometimes, I think, 1 microsecond or less than picosecond also. And in picosecond, they will be now shooting out pulses from inside, electromagnetic pulses, and we will be able to detect those pulses. So those pulses are so much tuned, so much perfect. For example, every pulse, if you are receiving from some space, and those pulses are coming out always from the same direction and with same time interval, is it not a surprising phenomena that why we are getting exactly same time interval? And that time interval is also so precise that it is of the order of 1 by 10 raised to power 6 seconds, or sorry, it is also large. Means picosecond. Picosecond is stands for minus 12 seconds.
10 minus 12,
minus 12 seconds. Sometimes this depends. Sometimes stands for minus 9. Sometimes maybe stands for minus 6. Depends on the size of the star. And but if star is very, very small, then time period becomes very, very less. And if time period becomes very, very less, as a result, it starts shooting out after every time period. After every one full turn, it sends one pulse of energy. And those pulses we are receiving on Earth. And those we call as those stars shooting pulses, which are shooting pulses of energy. We call those as pulsars. If you want to read something about it, you can read, but no need although. But I'm telling you, it is really very, very interesting phenomena there in physics in reality. So these questions which we are studying, sometimes these will appear hypothetical, but they have a very, very large, vast amount of significance. and some significance you will come to know up to in 12th class only, but some other questions, their significance you will not even know now. You will know maybe in graduation or later on if you study physics. Yeah. This thing is fourth example. Fourth example was of sun around which Earth is rotating. Now you notice force acting on the Earth passes to the center of the Earth. Force acting on the Earth passes to the center of the Earth. Then definitely torque to the center of
the sun.
So torque acting about the center of sun will be zero. So angular momentum will be conserved, but it will be conserved about the of Earth will not be conserved. But about the center of sun, angular momentum of Earth will always be conserved about the center of sun, because wherever Earth goes, but the force will always be towards the center of sun. So therefore torque always will be zero. If torque is always zero, then angular momentum will always be remaining constant in magnitude as well as in direction. And because it remains in constant in direction, it has also wonderful significance. If angular momentum remains constant in magnitude as well as in direction, by just constancy of direction, we can predict that the Earth will revolve around the sun always in one plane. Its plane of motion cannot change, because if its plane of motion changes, then angular momentum will change its direction, and angular momentum cannot change the direction, so its plane of motion will always remain same. Earth will always revolve around sun in one plane, and that plane cannot change. It is interesting phenomena again. Okay. Anyway, number 5. So many examples I can give. This example is also very important, and I should give it now only. This one. And this body is given a sudden impulse by which it gains velocity v, but it has no angular velocity. Then there will be friction on it, and that side, and mg will be downside. If I take any point here, then at any point here, will the torque be zero or not? On this place, means this P point could be here, or here, or here, or here,
Yes,
or
sir.
here.
Yes,
Or
sir.
here. I know all of you know that about this it will be zero.
Yes, sir.
Yes, sir.
Because normal and mg and force passes, friction force passes with this. But you don't know that about this point also it may be zero.
Sir, you said, sir.
Yes, sir. Because n equal to mg.
Why it is zero about this point? Because normal is equal to
mg.
mg. So their torques will cancel. If their torques cancel each other, normal will give us this kind of torque. Mg will give us this kind of torque, and their torques are equal in magnitude and opposite in direction. So they are cancelling. So we are left with mu n. But due to mu n torque, due to about P point is zero. So therefore torque about any point on this line, if it is a horizontal line, it should be horizontal. Horizontal is important here. If it is not horizontal, if it is inclined, then line of mg will not pass through point P. Then line of mg will be not passing through P point. So there will be some unbalanced torque. So it should be a horizontal line. That is important here.
Sir, you said about any point on a line parallel to LOV.
I said this thing before, not this thing, but I'm telling you. I said that about any point parallel to LOV, the angular momentum will be same, but I did not say it will remain constant with time also. That I said that about any point angular momentum will be same, but I did not say that it will remain constant with time. But yes, you can argue this way also. Yes, that is also one way of telling that about this point, it is conserved, and it is same also at all other points also, because angular momentum about this point and angular momentum about other points is also same. So yes, we can think somewhat that. But last time I said this thing that angular momentum about all the points parallel to LOV will be same, but I did not say, which I am saying now, that in this case that angular momentum will remain constant with time as this moves. If it remains constant with time, what is angular momentum now? I think everybody can tell me quickly, because omega is zero initially, it was given to be zero here. Then I think you can tell that angular momentum about P point, will be having one term. What is the total angular momentum term? Total is R cross M into VCM. Don't forget it, plus ICM into omega. This is total. But in this second term is zero, and first term only remains. And first term is, I think, taking MV into R perpendicular. I can write it as M into VCM into R perpendicular. That is, if it is radius R, then it is just M into V into R. And direction, about this point, direction will be clockwise. This is it. But do you know that it depends on M, R, and V? Does the V change or not? Does the V change or not? Yes, it changes definitely. Why? Because of the friction, it becomes less. If it becomes less, then how can the angular momentum be conserved? I said angular momentum remains conserved. How can it be conserved?
Angular velocity. It will change
Yes,
into
angular velocity it gains. Yes, very
Yes,
good. This boy understood it right, exactly right. I wanted to hear that. Angular momentum does not only depend on the first term, it depends on the second term. Here, second term is 0. But as soon as the velocity decreases, there is a torque about the center of mass. You can notice it, and that torque will provide it angular velocity in clockwise direction. So velocity is decreasing. So the angular momentum in clockwise direction is decreasing, but same decrease is compensated by the increase in angular velocity. So yes, it is true that this, let us say it was initially V naught, this plus ICM into omega will remain equal to initial value, that is M into V naught into R. That is the conservation of angular momentum.
So, sir,
Yes.
here we can say that then friction is converting a translation energy into rotational energy also.
Rather than saying that, why don't you say, that will be better if you say that friction is converting the one part of angular momentum into the other part of angular momentum. That I will prefer, because I know angular momentum is conserved. I did not say that kinetic energy is conserved. Kinetic energy is conserved. Kinetic energy is getting lost. So the friction is not converting the kinetic energy into rotational kinetic energy only. It is also that friction is converting the transition kinetic energy into two forms of energy: heat energy and rotational kinetic energy. That we can say.
Okay, sir.
Okay.
Yes, sir.
Right. So this one example, another example of similar type only. Let us call it 5A and the other is 5B, because these are so similar. So I will prefer to. Why don't I write the question here itself? I did not write the question. Let us write the question and finish this chapter here itself. I don't want to deal with it again. This I can write as I1 omega 1 plus I2 omega 2 is equal to I1 plus, in general, if there are one after the other, several are falling on each other, then I can say omega will be equal to sigma I omega I divided by sigma II. This we can say in general. Okay, if there are many other disks also coming one on the other, then we can say like this. What about first man person, this man's case holding dumbbells? Then we have to specify something that his moment of inertia changes from I2 to I1. Then I can say I2 omega 2 will be equal to I1 omega 1. But somebody should give me that how his moment of inertia changes. If they are not giving, then they can ask only conceptual question, but they cannot ask any numerical. If they just simply say that when man folds his hand closer towards himself, then what happens to omega? Then I will say omega moment of inertia decreases and then omega increases. Then it is just a conceptual question. Shrinking earth question, in this I can ask numerical. I can say radius of earth becomes half. If radius becomes half, moment of inertia is proportional to r square, mass remains same. So moment of inertia becomes 1/4. Moment of inertia becomes 1/4, then omega becomes 4 times omega. And if omega becomes 4 times omega, then time period becomes t by 4. Then duration of day will become 6 hours duration of day. Then day will become 6 hours. Understood?
Understood.
So this way we can do, means just by proportionality, we can do it. This example of sun, earth revolving around the sun. In this case, angular momentum is conserved, and we will discuss it in detail in gravitation chapter. So let us leave it for that time. This part you understood already. One more part now coming here, and that is initially I'm rotating it with angular velocity omega this time, and then releasing it on the surface, just releasing it gently on the surface. If I do that, one more thing here, why don't I just do it completely rather than leaving it here? 5A. In 5A, I should not end it here. There are many questions which we can ask in this. But always this thing which I said will be valid. But what other questions I can ask? I can ask other questions. Find final angular speed or final speed when pure rolling starts. When pure rolling starts, then what happens? Then relative slipping will become 0. If there is no relative slipping, then friction force will become 0 in that case. Then friction force will become 0. Does it mean when there is a pure rolling, friction force has to be 0? Not like that. We have seen already in inclined plane. In inclined plane, even though it is pure rolling, but that is having acceleration. It is, we call it as accelerated pure rolling. It has some acceleration. So pure rolling is possible even when friction is also, when pure rolling also friction may be acting. That may not be 0. But I don't know you remember the formula for friction or not. But when I found this friction, I have seen one thing, that this friction comes out to be proportional to sine theta. That theta is the angle of incline. And when theta becomes 0, then friction will also become 0. So if pure rolling is taking place, on a ground without application of external force also, there is no external force here, remember. Just no external horizontal force, I should say. External forces are there, normal is there, mg is there, but there is no external horizontal force. Then in that case, friction finally becomes 0. Not always, but in those cases, friction finally will become 0. So in our present scenario, which we are discussing, in our present case, what happens here, see, the velocity decreases, omega increases, and a time will come when v will become equal to r omega. And when v becomes equal to r omega, something like this. Let us say I want to plot v versus time graph, and I want to plot r omega versus time graph. So velocity starts from v0 and it is decreasing, and r omega starts from 0. It was 0 initially and it is increasing. But there will be a time t0 when this v will become equal to r omega. And when that time is there, after that
will both equal.
Neither v0 changes nor r omega changes, then this will become constant. So let me clarify further which graph is representing what. This graph is representing velocity, and one more graph I need here, r omega graph. R omega is also in the same axis only, but it starts from here and then it becomes like this. This is r omega graph. You understand now?
Yes.
Means after that it is overlapping line, but this overlapping line is representing r omega as well as v, because these two are equal. So when that happens, then it is pure rolling. So what they can ask this thing also. At what time t0 the pure rolling starts? They can ask this thing, or they can ask what is the final angular velocity, this thing, finally angular velocity or final velocity vf, or whatever you want to call final one. Let us call it v only maybe. And final angular velocity, final omega, what it is, they want to find that. Can we find it? Yes, we can find. How? Because initial angular momentum was conservation of angular momentum again. Final is equal to initial. What was the initial angular momentum? Just m into v0 into r, as you know. What is final? As I told you before several times, it is beta into m into v into r. This time I'm doing it in faster, quickly I'm writing it. I'm not even writing ip into omega, because you know this thing is ip into omega only. If you write ip into omega, that will become beta m into v into r, where ip is equal to beta m r square according to my own notation, right? So means finally, if it will be pure rolling about p point. So finally, angular momentum about any point, this point p and that point which is here, this will be same. And about this instantaneous center of rotation, we already know that will be nothing but just ip into omega, and that will be nothing but beta m r square into omega. That will be finally, let us call it p dash point, and that will be equal to beta m into v into r, because v is also equal to r omega. Is it understood by you?
Yes, sir, pure rolling condition.
So I think you understand it. Then can you write it the way I wrote it very fast? This one you should write it. I don't expect you to slowly keep finding, and this time quickly, very fast. We can write v is becoming equal to v0 divided by beta. Right or not?
Yes, sir.
Once you know this, can you find out what time it takes to achieve that? Time is easy to find out, but for that, angular momentum conservation will not be helpful only. That is required, but that we already used. Now we have to use something else. Acceleration. It is because of F upon M is acceleration, and mu mg upon M, that will be mu g. Because why mu mg? Because it was sliding in the beginning. We know acceleration is this. In fact, and then I can write with minus sign because it is magnitude. It will be with minus sign. So I can write V is equal to V naught minus mu G into T naught. T naught is that time when the pure rolling starts here. T naught is the time for the pure rolling to start. So I hope you can do it now. Can you?
Yes, sir.
What is time T naught? T naught is coming out to be V naught minus V naught by beta divided by mu G simply. That is V naught into beta minus 1, that is eta. V naught into eta by beta into mu G. Beta minus 1 I call as eta.
Eta V naught by beta mu G.
Yes, eta V naught by beta. Eta by beta we are multiplying. This eta by beta factor I have seen somewhere else also. Oh no, that was I think beta by eta. This time it is eta by beta. That time it was beta by eta. That was coming when I was
Tan
discussing angle of repose. And angle at the sliding starts. Tan theta is equal to beta into
beta by eta.
Minimum
beta
angle
into,
for slide.
that was minimum angle for sliding. Beta into mu by eta. But now it is eta into. I think it is coming out in that terms only. By chance I am noticing now. See, if I write it as beta into mu by eta, then it is coming out in that angle terms only. Whatever that angle is called, let's call that angle as we don't call it angle of repose actually. But if it is, let us say, apparent angle of repose, I should say, or something different, or our angle of repose means we are only defining it in that way, then we can write it in this form also. And it is coming out to be in that terms. Then this will be like tan theta into G. It is coming out in that form only, right or not? Second question. I will come to this again. But before that, you may be thinking, what is left now? See, there is no limit to the questions which we can ask. We can ask many other questions also. For example, if I want to ask, I can ask. I can ask here. Kinetic energy lost or work done by friction. What will be work done by friction? Work done by friction will be equal to change in kinetic energy, or we can say final kinetic energy minus initial kinetic energy. As there is no change in potential energy, normally work done by non-conservative force is equal to change in mechanical energy. But here potential energy remains same, so we can write just kf minus ki. Right or not?
Yes, sir.
Yes, sir.
Right. We can do this. So now second example was this similar question, but somewhat different from that. If this time I'm just giving it initial angular velocity, but V naught was not there. That was zero only. No initial velocity was given. Just omega was given. Omega naught was given, and it is just gently kept on the ground. The moment we keep it, it is rough surface. Horizontal surface, mu is there. R, M, beta, etc. All things are given. ICM is equal to eta mr square as usual always, and IP is equal to P is this bottommost point, and that is equal to beta into mr square. So can the conservation of angular momentum be applied again or not this time? Normal upwards, mg downwards. Notice why I am taking mu n this time in forward direction. Reason is r omega backwards, but mu n will be opposing that, so it will be forward. It will be this side. Right? Right or not?
Yes, sir.
Right. We can give initially both also. Means I can give next time I will give that situation where I will be giving V naught as well as omega naught, and I will ask you how to do. So what to do next in this case now? Same thing as we do. Please, I am expecting you to do before I finish. Why don't you do yourself only? What will be the final angular momentum during pure rolling? During pure rolling, always one formula only. We don't even have to worry. Quickly we can apply that. What is the final one? As I did before, you can quickly apply it. Final. Let us say final velocity is v. Beta mvr quickly is equal to initially there is no first term RC r cross m into VCM term is not there.
Omega naught.
R cross m into VCM term is not there. That is 0. Then only we are having ICM into omega term initially. Then I can write it as eta into mr square into omega naught. That on. Then I am getting v is equal to eta upon beta into r omega naught. I think that only. Right or not?
Sir.
Right. Next. Other things also can be there. Which other things are there? In this case, what is happening here? If I plot velocity and those graphs, if I plot, then I think velocity and r omega graphs I want to plot. This time, r omega was initially there. That was r omega naught. But it decreases. And velocity was initially 0 and it increases. And then finally, become constant again at time t naught, which I can again obtain. How to obtain t naught this time?
So
This
then
time
why
What?
didn't we take omega? Why didn't we take omega finally, sir? There will be some omega no, sir.
Oh my
Finally.
God, this boy is still, oh my God, really unfortunate. Final omega, why we are not taking final omega? This is beta MVR. Beta, what is beta here? Beta we take when we take the moment of inertia about the bottom point, and when we take that, then it is already including both rotation as well as translation components together. It has included both the parts. Please learn these things now only. Now also you are forgetting. Now only you are forgetting. How will you remember this for long? This is including both. It is including ICM omega as well as m into v sum into r. If you are doubtful, you can take that, and then you can see that we are getting same result only.
We already did that.
We have done several times although, but okay, still, whenever doubt comes, I recommend you, whenever you have doubt in any one formula, it is a general rule, go one step back. Where we got that formula from, go to that and then apply from that, start from that. If you are having formula in that doubt, that form also, then again go one step back. Keep on going one step back. If you keep on doing this way, keep on going one step back, then at last you will be reaching always either in some definition or in some law. And we cannot go beyond law.
Yes,
and we cannot go beyond definition. Definition is just we defined it in that. Okay.
Yes, sir.
Right. Now, this is also done, and same things will be changing velocity. Whatever they ask now, you can find out all those things like this. Yes. I don't know what are you saying, but okay, let me continue. Next, I can say
It's time T naught.
T naught. Oh, how to find T naught? T naught we can find out by we know velocity increases, and this time it is equal to mu g times mu g supporting it. It is mu g times T naught,
And V equals to R omega.
and V is equal to R omega. So I can write it as what should I write next? I have got V, and V is equal to R omega. Then I can write it as R omega also. R omega is equal to mu g. No, wait a second. What am I doing now? I got T naught from here only. T naught is equal to V by mu g. So I am getting now. eta r into omega naught divided by mu g into beta.
Beta.
That is T naught. Okay.
Yes, sir.
Somewhat different case again. Some little modification will keep on making, and see the question will keep on becoming tougher and tougher. But it will become tough after slight modifications. If you make, you will never find it to be tough. You will think it is same question only being discussed again and again. But somewhat changes I am making. See, now I am introducing one plank. I think this does not look like a plank. It's like a plank. So now it is kept on a plank, and the whole thing is again on a smooth. No, not smooth. Yes, smooth is better. Smooth horizontal surface. After that, I will remove the condition of being smooth also, and then we'll see what happens. Right now, I'm taking the condition when it is smooth surface. Mu is 0. This is m, and this is r radius, and this is capital M, and of sufficient length. Somebody may think that pure rolling will not start, and this whatever disk or whatever this rolling body is, it will fall from the plank. I am assuming it will not never fall from the plank because plank is very long. So assuming long plank, is it okay? Now, what case I am asking you? There are how many cases possible? I discussed 2 cases. In fact, 3 cases are also possible. I did not take that one. I could have taken, oh my God, so many things are there. I can take that one also. What should I do? Okay, I will take that one first maybe. It has angular velocity omega, sorry. Angular velocity omega naught, and it has velocity v. And it is kept on the surface. Question is, in which direction finally will it be going? In which direction finally will it be going? Left hand side, right hand side, or nowhere? Or depends?
It depends upon V and omega, sir.
Yeah, exactly right. You understood it. How will it depend?
Sir, if omega is more, it will move forward, sir. If velocity is more,
No. Very, very simplistic view, not that. Remember one thing. I will take 2 examples from here, and I will tell you which of these will be possible. What will be the final fate of it? Let me discuss those final fates. One possibility, second possibility, third possibility. There are 3 possibilities. 1, 2, 3. And the possibilities are these. Finally, it may be moving in, it may be rolling, forward rolling. And no rolling, backward rolling. It may finally stop.
yes,
It
sir.
is rolling in forward direction rolling. Although what is forward and backward depends. Actually, I think we should not call it forward. Normally, we say opposite to velocity we call as forward. Because in this velocity was initially in this direction. So this direction we'll start calling as forward. And then opposite to that will become backward automatically. So that is called it forward rolling. Forward rolling. Forward means, I am clarifying again, it is in our present case, it is right side, but it is not always right side. But because I assumed in the diagram that this diagram it is velocity in the beginning question, this velocity was in this direction. Therefore, our right side will become forward. Normally, this side is forward. Normally, if nothing is mentioned, then we will call this side as forward, right? I am saying right side rolling, and it is rolling right or left. I should say. What am I doing? I am saying opposite. Left side rolling. No, it is left side. It's going towards left. Initially, also it was towards left. And then it is the other possibility, backward rolling, which I will call this time as backward. Backward means it will return. It will initially going to the left, but finally it will start coming to the right. So it will return from somewhere, right side. Okay. I can ask this question in another way also. what will be the relation between V and omega naught, so that this crosses the point where it lands. Now it crosses this point again. So it can cross this point again only if it returns back. So if it has to return back, then it should be finally backward rolling.
Yes, sir.
Or there may be a case of stopping, or there may be a case of forward rolling. How to tell which case it is? Let me tell you a very simple way. That is the simplest way to tell. No, it's cross means anti-clockwise. No, cross means, sorry. Finally, it is not cross, it is dot, and it is cross, I think, right? Notice this angular momentum is in cross direction or not. Omega is.
Yes, sir.
If it is pure rolling, then in pure rolling case, we don't have to worry about velocity term, because in pure rolling, both angular momentums will always be. Just add it up. They will not subtract. They will not cancel each other. They will add up only. If it is clockwise, then effect of velocity will also be in the same way only. You understand what I mean to say? Means if omega is clockwise, then angular velocity, then due to velocity also about this point, that also will become clockwise only. If omega is anti-clockwise, then due to V also it will be anti-clockwise only. So this will only add up. This will not subtract. In pure rolling, it will happen always like that only.
In pure rolling.
Therefore, I think we are able to reach the conclusion that if initial this angular momentum we know remains conserved. If angular momentum remains conserved, then if initially angular momentum was in cross direction, then finally also it will continue to be in cross direction. If initially it was in dot direction, finally also it will continue to be in dot direction. So what is the condition for angular momentum to be in cross direction? If angular momentum is in cross direction, then which should be greater? Which is representing cross here and which is representing dot? I think we can see
Omega naught
that
is
about P point, omega naught is representing cross, and this one is representing dot. So ICM into omega naught is in cross direction, and M into V naught into R is in dot direction. If MV naught R is magnitude wise greater than ICM into omega naught, then finally dot will win and it will remain in dot direction only. So this case will be when it is MV naught R minus ICM into omega naught.
ICM into omega naught
is positive.
Then dot direction.
That is in dot direction, and that should be positive here. And this one will be when ICM into omega naught minus M into V naught R. That should be positive. That should be positive. Then this will be the case. So what we will do, we will put in both cases, we will put finally these things as beta into M into V R. Here also we will put it equal to beta into M into V into R. So we can get that way only, the way we normally get. But in one case it will be forward rolling, in one case it will be backward rolling. That will be the case. And in this case, in our L equal to 0 case, in L equal to 0 case, beta MVR will be 0. So V will be 0. So it will be finally coming to rest. It will not go anywhere. Understood these three cases?
Understood, sir.
Very good. Very good. Very good. Very good. So now,
sir,
what?
In minutes also over.
Oh, time is over. Time is over. Then
12:55, sir. Time.
Then can we end? What about evening? Can we take in the evening or?
Carry on, so you can take.
Or tomorrow?
Yes, sir. Yes, sir.
Tomorrow.
Your wish.
We have a revision, sir.
Yes, we are not that much. No problem is not there. I can do tomorrow also. So if we, your
Sir,
choice.
it is better to complete theory first and then we can do problem.
Then I will pray today only. I will do. Then
Yes,
today
sir.
evening I will take class. Okay. That will be better then.
Sir.
Okay. Yes.
Okay,
After
sir.
completion of evening class, once take all summaries.
Yes, so no problem. I will take. Don't worry. You remind me at that time, but okay, because I will forget otherwise. You remind me at that time. If you take something, I will take it. Yes.
Sir, I have a doubt.
Yes, ask.
Sir, we discussed we discussed one problem, sir, school problem on Friday.
Which problem I discussed?
School, sir, I
School,
said.
school problem I discussed,
Problem,
right?
sir. A,
Yes.
A and B, which Nilakanta sent you about. In that I have doubts, sir.
What is your doubt? Ask me that doubt.
Once go to the diagram, sir.
Okay, wait a second. Let me just prepare myself for the evening class. One thing I want to take, and because right now with the flow, I know what should I take, and after that I may lose the flow and I will forget what I have to take. So therefore, let me show the diagram here. Now I want to make it more tougher and tougher. No, so I will make it tougher by this way also. I will make it tougher, but I will keep it fixed. Don't worry, I will keep it fixed. Angular momentum will not be conserved in this case. I'm moving from conservation to non-conservation cases. In this case, angular momentum will not be conserved now. But we can ask this thing that if it is initially having angular velocity omega naught, up to what height will it go? Or if it is initially having velocity v naught, up to what height will it go? Those things I can ask. Those things I can discuss. Two questions I can discuss here. After that, if I want to make more complicated, then I will make it movable. So I can make it fixed. One case A fixed, case 2, it is mu equal to 0 in the ground, so it can move. Those will be again somewhat interesting cases, and we can discuss those. Yes, now I will come to your question. What was that? Wait. One more thing is very important here, and that is platform cases of platforms. That also I will be taking tomorrow. If a man jumps off the platform in different directions, this side at an angle theta, or in tangentially or radially, what do we get? Or when they don't jump, but they just move around from one place to the other place. Man goes from here to here, comes from here to here. In this case, one case,
Platform will
cycling
get
case.
rotational motion, sir.
Platform will get rotation where the platform will stop. Man comes by an angle theta, then what will be the angle of platform? Man is having theta naught angle. What is angle of the platform? Moment of inertia, etc. Given these cases. Then one more case is there in this, which is of when there is a retarding force proportional to angular velocity, k omega torque. Retarding torque is there, k omega minus k omega. Then in that case, what happens? These three cases also I will deal with. And after that, I will start collisions. And collisions, I don't think I can cover today. Maybe tomorrow I will start, or if possible, or maybe I can do one thing. I think in this I'm going too deep. This is in depth. I can leave it for the timing. This is basic. I will do the basics first. Number one, I will do. After that, one basic question I will take from here, and then after that, I will jump on to the collisions. More difficult ones I will take for the at last, right? Now I will come to your question. So that if I have covered the basics, you can start doing the problems, and then difficult questions we can do later on also, no problem. Yes, now you tell me which question you were asking.
So you have
School
gone.
problem, sir. Which have two radius, inner radius and outer radius. A and B.
This one.
This problem. This one.
Yes.
Sir, go sum up, sir.
Yes.
Upward. Yes, sir. Here we have taken T into B minus A equal to IP into
Yes.
alpha, sir. We had taken acceleration R alpha, means you have taken R equal to B minus A y, sir.
Yes.
Because the center of mass is rotated at the center, no,
This
sir, not at the point A.
I'm not saying center.
Then how can we take B
Who
minus
said?
alpha?
Listen. Where did I write center of mass acceleration as R alpha? I wrote for this mass. This mass is attached to this part here. Is it attached to the center? This mass is, see, this mass
No,
has
sir.
same as that of string, and string has here B minus alpha. So I'm writing for the string. Here I'm clearly mentioning it is AA, acceleration of A point. It is only acceleration of A point. I did not say it here. And here I'm writing for the center, it is B alpha. If I have to write the equation for this spool, translatory motion equation for this spool, let us say I want to write the translatory motion equation for this spool. And let us say external force acting on it is F and T and F and T. Then I will write F plus T is equal to capital M, then I will write into B alpha only.
Yes, sir.
Okay.
Yes, sir. Okay, sir. Okay, sir. Understood.
All right. That's it.
Yes, sir. Okay, sir.
Okay, then let us end it now.
Bye, sir. Thank you, sir.
Bye.
Yes, sir.
Bye.